Hello everybody, my name is Chawki Awada. I'm an associate professor of physics at Physics Department College of Science here in Faisal University. Today we will talk about how can incorporating silver and multi-wall carbon nanotubes in lithium niobate tailor its band gap. We present here the outline. So we will start by an overview of the introduction by mentioning, presenting more the challenge and motivation and the objective of our work. And how can we narrow the lithium niobate band gap by mixing Ln with multi-wall carbon CNT and silver. This will open the way for solar diving photocatalysis application. At the end, we will finish with some point concerning the conclusions and perspective. So lithium niobate is a trigonal and non-centrosymmetric crystal with important physical property. We know at below the Curie temperature 1210 degrees Celsius, it has a ferroelectric phase, and the lithium and niobium atom is shifted from the plane where the oxygen atoms are placed, and this will create a permanent polarization, and this is polarization stay even we excite the system with electric field, and in turn will promote important physical properties like, for example, electro-optic and acousto-optic properties that make it essential in telecommunication, waveguide devices, and nonlinear optics. So it can be considered like a silicon of in waveguide devices. However, due to the polarity effect, it started in the last year attracted a lot of attention for photocatalysis application, like, for example, also water splitting for hydrogen production, and also for solar cell application. One of the most challenges related to its wide band gap that limit visible light use. That is why it is important to adopt with noble metal like silver. We know that noble metal like silver and gold possess an interesting properties we call surface plasmon resonance, and this will shift and extend the absorption of the semiconductor. But it is not sufficient. It is important also to increase the conductivity and reduce the recombination rates. That is why we can add the light carbon nanotube. So in this work, our objective to fabricate a new nanocomposite hydrothermally, and we use photodegradation of a complex dye to test the photocatalytic activity of the new system. Structural and optical DFT study were also carried out in order to investigate the effect of the new element on its optical and electronic properties. So I will show you here the fabrication process. There are different steps. By starting mixing the niobium hydroxide with lithium pentanedionate in 40 milliliter ionized water, we stirred for during 6 hours. After 6 hours stirring, we put them in the autoclave stainless steel for 86 hours during 220 degrees Celsius. And after decanting and centrifuging, we obtained the pure Ln clean Ln powder, and we mix them with silver nanoparticles fabricated chemically, and also multi-wall carbon nanotube using CVD. So then we make a stirring, also centrifuging and decanting with water and ethanol for different steps, and at the end we dry them at 70 degrees Celsius to remove the moisture. And moisture, can be used for the characterization. So the first characterization was the transmission electron microscopy. It is important to see the morphology and to quantify to evaluate the size of the nanoparticle obtained. If now we can, for example, look at the different image. In the top it is the lower magnification, however in the bottom it is higher magnification. We can see more dispersed and then for the pristine. However, when we add silver, it increased a little bit, and also the size stayed close to the previous the silver. However, when we add more carbon nanotube, you can see clearly the carbon nanotube is a diameter of 2 nanometer, or with also LN nanoparticles, however, with smaller than the 1% and the adjusted AgLN. So for the ADX, it was energy dispersive X-ray were performed in order to identify the element. For the pristine, we can see the niobium, the carbon, however, the lithium, because it cannot be absorbed by the gas, because it's light mass. For the now, when adding silver, you can identify the presence of the silver atom. And for adding carbon, the carbon also increased for the case for 1% carbon nanotube, and also increased again when we add 5% multiwall carbon nanotube. To identify the crystal structure and the type of phase, we performed the X-ray, we measured the XRD pattern for the 4 sample, and also we added the commercial. Why commercial? Because it is a pure LN, we need to compare with it. So the most of the XRD pattern LN phase were observed with a little bit shift, as this is normal because the nanoparticle is small, and also there is a compressive stress. This can be responsible for this kind of distortion. In addition, what it was surprised that the LN pure and the Ag 5% presented the higher crystallinity than AgLN, Ag 1%, and this is confirmed here by when we fitted also for example, the 1012 crystal plane. We can see the size increased when we add Ag 1%, and after decrease we'll add 5. As this is correlate well with the value observed by TEM. So Raman spectroscopy is a complementary study because we know the LN is non-centrosymmetric. So and Raman is very sensitive to any change and any for the different for the mode. So different Raman mode are active is when we have non-centrosymmetric crystal. If, for example, we see the dashed line here show the LN, the phonon mode related to LN phase. We can see also other mode like, for example, LINB308. Like, for example, if we can see, for example, this is a rhombus. We can also see the presence of DG band related to confirm the presence of carbon nanotube. And the star also, this is confirmed the presence of another phase, it is Li3 and BO4. So the Raman peak position was measured also. The Raman peak, we can see a red shift, sorry, to AgLN, Ag1, and after it the blue shifted, and this is confirmed also the lower crystallinity observed in the XRD, and so it can be clearly seen the correlation between the Raman and the TEM. To evaluate, to quantify the band gap, we measure the absorbance as function of wavelength. We can see more expansion extending due to the plasmon of carbon nanotube, especially near the UV. However, for the visible, it was also extended more, and more increase also when we add more carbon nanotube. This is explained that the carbon nanotube in conjunction with silver will be more. The silver will also has a strong effect in increasing the absorbance. We use the top plot for direct band gap to quantify the band gap value. Here the band gap value decreased by adding Ag and Ag. We reached to approximately 2.8 electron volts. So from 3.8 to 2.8, so approximately it decreased 1 electron volts, and this is very important and can be used for solar for solar driving photocatalysis application, or any, for example, application where we can use UV visible sources. Now, for the application, we use the RB5 dye as a complex dye. We measure the absorbance as function of wavelength for different radiation time in order to see quantify the degradation efficiency, to measure degradation efficiency. We can see the Ag 5% CNT more fast than AGLN and LN and the other. However, both AGLN and AG 1%, due to its low crystallinity, they still low, and this can be sure correlate with the large size, and also the low crystallinity measured during the XRD. And I guess that here the surface to volume ratio here play an important role, because the size here is large for both, and this is affect the photocatalytic activity. Now, for the kinetic study, we plot the Ln concentration C over C0 or radiation time to extract the first order rate constant. We can present here the different value on this table. For example, we take the K1. We can see for Ag, if you compare the Ag 5% CNTLN, it is more 7, 9, and for 10⁻³ and also 3, 10⁻³. So it is 2.5 approximately from Ln. However, for the medium, it is low due to the size effect, the large size. Now we can explain that the photocatalytic mechanism by exciting or irradiating UV visible light to the semiconductor. We can create whole electron that react with the oxygen and water to generate oxidizing agent, and in turn this can react to give CO2 and H2. We also performed the theoretical study to explain why the band gap narrowed, become small or reduced for different configuration, pristine and Ag at the NB site, and also interstitial sites, and also heterostructure, and also by adding to the B configuration carbon. For example, if we look at the energy density, we can see here the band gap between the valence and conduction band is 3.9. This is undirected band gap. And however, when we add the silver, we can create mid-state, and this is reduce the band gap. For the case of interstitial, we can see a shifting of low Fermi level. And the band gap also reduced from 3.9 to 3.6. From the case of nano for heterostructure, there is a more reducing and more occurrence of impurity state. And when we add carbon also for the B configuration, like carbon nanotube, it becomes more conductor, and there is occurrence of more of mid state. If we look now for the dose state, we can observe clearly for pristine the contribution of oxygen P and for the conduction for the valence. However, the NB can be contributed to the conduction. When we add silver, with the AgD can contribute in the mid state, and it will be close to the valence band and above the Fermi level. It can be also hybridized with the OP state. For the now, this is also for concerning the interstitial. It can be shifted the band gap as mentioned in the energy state. However, for the heterostructure, we can see more state related to Ag جديد between the conduction band and valence band. By adding more carbon, the carbon also P and carbon S and Ag can also be more impurity state can be added, and this is can narrow enough to make it more conductor. To conclude, we successfully narrowed the optical band gap of length with the incorporation of multi-wall carbon and silver. The alien nano composite showed fast kinetic of photodegradation. This nanocomposite will open the way for new solar-based application, like for example water splitting for hydrogen production. Thank you very much for your attention.